In this video, I'm going to discuss the intrinsic definition of the covariant derivative. This is a continuation of videos 17 and 18 where I discussed the flat space and curved space definitions of the covariant derivative, so please watch those first if you haven't already. The links to those videos are in the description. I'm also going to talk a little bit about geodesics in this video, but my main videos on geodesics are videos 15 and 16, so check those out if you want to learn about geodesics. So previously we learned that the covariant derivative on a curved surface is the rate of change of a vector field v in some direction w with the normal component of the rate of change subtracted. So this is the covariant derivative in the direction of the u coordinate, and we can also write it using this expression where the Christoffel symbols represent this formula. We also learned that when the covariant derivative is 0, it means we're parallel transporting a vector along a curve, and I showed you some examples of what parallel transport looks like. And one viewer actually sent me this animation which conveys parallel transport on the sphere really nicely. There's a link to this animation in the description. So in this video, we're going to move on to our third definition of the covariant derivative, which is the intrinsic definition for curved spaces. So I'm just going to quickly remind you that there's generally two ways of looking at curved spaces. There's the extrinsic approach, where you look at a curved surface living in 3D space, and you often work with x, y, z coordinates and 3D position vectors. Then there's also the intrinsic approach, where you pretend like you're a little bug that lives on the surface, and you have no idea that the outside world exists. So instead of working with x, y, z coordinates in 3D, you would only work with the coordinate lines on the surface, labeled here as u and v. And for this video, instead of calling the coordinates u and v, I'm going to be calling them u1 and u2 instead. So when it comes to intrinsic geometry, a lot of what we've learned about the covariant derivative is still the same. The formula is still the same, and the concept of parallel transport is still the same. The thing that's going to change, however, is our formula for the Christoffel symbols. You'll notice that the formula for the Christoffel symbols has a dot product in it, and this dot product is actually a big problem for intrinsic space. Previously, when we calculated the Christoffel symbols on the sphere, we expanded all the basis vectors and basis vector derivatives out in terms of the xyz basis. And doing this expansion is what let us compute the dot products. But now, with intrinsic space, we basically have to pretend that the xyz variables don't exist. We can only see the coordinate lines directly on the surface, so we can't expand these vectors out in terms of xyz, and so getting the Christoffel symbols is going to be more difficult in intrinsic geometry. Now, before I show you how to compute the Christoffel symbols, I think it's worth asking why we should care about intrinsic geometry in the first place. I mean, if extrinsic geometry gets the job done, why would we bother making our lives more difficult with intrinsic geometry? Well, one of the main applications of the covariant derivative is in general relativity, where spacetime is a curved four-dimensional space. And when Einstein came up with general relativity, he did not think of four-dimensional spacetime as living in some sort of higher dimensional space. He didn't make up some higher dimensional origin that we could use to point position vectors at our universe. He just thought of spacetime as intrinsically curved, with no outside space existing outside our universe at all. So it's important for us to study intrinsically curved spaces, because they'll help us understand four-dimensional curved spacetime. And that means we're going to have to abandon the idea of extrinsic xyz coordinates and the origin, and position vectors that extend from the origin. All we really have is a space with curved coordinate lines. So this brings up one of the main differences between extrinsic and intrinsic spaces. In extrinsic geometry, we define basis vectors as the rate of change of a position vector capital R along curves. So the basis vectors end up being the tangent vectors along the curve. But now with intrinsic geometry, we don't really have an origin that we can use to extend position vectors from, since the space is curved. So we can no longer think of basis vectors as derivatives of a position vector capital R, like we do in extrinsic geometry, where we work with vector spaces like R2 or R3. Instead, with intrinsic geometry, the basis vectors we're using are the partial derivative operators themselves. So these derivative operators point in a specific direction, just like ordinary vectors point in a specific direction. So these derivative operators would point in the directions of the u1 and u2 coordinates. And these basis vectors live in the vector space called the tangent vector space at some point P. So given a curved space M, there's a different tangent vector space, TPM, at every point P on the curved space. And we use M here to stand for the word manifold, and a manifold is basically just another word for a curved space. Okay, so let's start computing a formula for the covariant derivative for intrinsically curved spaces. So before we said that the covariant derivative of a vector field is just the ordinary derivative with the normal component of the rate of change subtracted. But since we're dealing with intrinsic geometry now, there's no such thing as the normal vector, since using normal vectors would imply that there's some sort of outside space that we can point into. So we're just going to ignore the normal vector part of this formula. So we just expand the vector field into its components and take the derivative using product rule. So we get a component derivative term and a basis vector derivative term. And recall previously that we expanded out this basis vector derivative as a linear combination of the basis vectors and the normal vector. But again, in intrinsic geometry, there's no such thing as the normal vector, so we just ignore this. So we expand the basis vector derivatives entirely in terms of the basis vectors, using the Christoffel symbols as the coefficients. And we could also write this using the Einstein summation like this. So subbing this in and changing this summation index here to k, we end up with this final expression for the covariant derivative. And this is pretty similar to what we saw before, but the problem ends up being with these Christoffel symbols. Before we derived an expression for the Christoffel symbols by taking the dot product on both sides with a basis vector, then doing a summation with the inverse metric tensor to get this formula. But again, the problem here is that we have a dot product of basis vectors and basis vector derivatives. And since we no longer have the XYZ extrinsic basis, we can't easily compute these dot products. So we need a new strategy for computing the Christoffel symbols. So to get the intrinsic version of the Christoffel symbol formula, we're going to need to recognize a couple facts. First, we need to remember that the metric tensor components are just the dot products of the basis vectors. And since the order of the dot product doesn't matter, the metric tensor components Gij are the same as the components Gji. So the metric tensor components are symmetric in the I and j indexes. And if you prefer writing things using the derivative operator notation for the basis vectors, you'd write things like this. And you might ask, well, how do we compute this dot product if we can't expand the vectors in XYZ space? Well, the metric tensor is so important that we require the dot products of EI and EJ to be defined for us. So we can either just declare a metric tensor that we already know, so like this metric tensor for the sphere, or sometimes the laws of physics can help us get the metric tensor, like we do here with the Einstein field equations in general relativity, which help us solve for the metric tensor components here. Either way, in intrinsic geometry, the metric tensor needs to be given to us somehow. The second thing I want you to notice is that the derivative of the EJ basis vector in the direction of the UI coordinate really just means this second order derivative here. And since the order of differentiation doesn't matter, that means that this is also equal to the derivative of the EI basis vector in the UJ direction. So if we look at these two basis vector derivative expressions expanded using the Christoffel symbols, and you'll notice that the I and j indexes are reversed here, since this derivative is equal to this derivative, that means that these two Christoffel symbols are the same. So the Christoffel symbols are symmetric in their lower indexes. If we swap the lower indexes, the Christoffel symbol stays the same. So given these two facts and a bit of mathematical ingenuity, we can actually solve for the Christoffel symbols. So we start by taking the derivative of the ij metric tensor components in the direction of the uk coordinate. And remember, the metric tensor is just the dot product of the basis vectors. Now, to differentiate this, we're going to sort of use a special version of the product rule that lets us do this. So this is sort of like the ordinary product rule where we have a sum of two terms. In the first term, the derivative is applied to the first factor, and in the second term, the derivative is applied to the second factor. The difference here is that this product rule is working for the dot product of vectors instead of working for ordinary multiplication. So the property that lets us do this is called metric compatibility. So this metric compatibility isn't too important right now, but it's going to be very important in the next video when I cover the abstract definition of the covariant derivative. Anyway, we can replace these basis vector derivatives with the Christoffel symbol formula, and the Christoffel symbols are just scalars, so we can take them out in front, and these dot products are just the metric tensor components. Now remember, we're free to switch the indexes of the metric tensor, so I'm going to go ahead and switch the L and J indexes of the metric tensor here. Okay, so we have this formula here where the derivative of the ij component of the metric tensor with respect to the k coordinate gives us this, with summations over the L index. Now I'm actually going to write out this same formula twice more, but with different indexes. So here I have the derivative of ki with respect to j, and here I have the derivative of jk with respect to I. And those would give us similar formulas, just with the ijk indexes shuffled around a bit. Now I'm going to color code the terms we have in these three formulas. You'll notice that the blue terms here are actually the same, right? Since we're free to swap the lower indexes of the Christoffel symbols, these two terms highlighted in blue are actually equal. And these red terms are also the same, again, since we can swap the lower indexes of the Christoffel symbols, and again, these green terms are also the same. So if we do this derivative plus this derivative minus this derivative, we'd get this. And looking at this expression, the blue terms cancel out, the green terms cancel out, and the red terms get added together. So we have this, and again, these red terms are the same, so I'm just going to combine them together. And I'm also going to sum on both sides with the inverse metric tensor, and that will cause the metric and inverse metric to cancel out and become a Kronecker delta on the left side here. And you'll notice I've also divided by 2 on both sides, so we get a factor of 1/2 over here. And using the Kronecker delta index cancellation rule, I can cancel the L's and write M, and we get this. So this is our new formula for the Christoffel symbols. And this completes our definition of the covariant derivative that works for any intrinsically curved space, as long as we're given the metric tensor. So let's do a sanity check and make sure this formula works. You'll remember in the last video we computed the Christoffel symbols on the sphere to be these. So let's recompute these symbols using the new formula. So we know the metric tensor for the sphere is this, and this would be the corresponding inverse metric tensor. Now if we took the derivative of these tensor components, the only non-zero term would be taking the derivative of the g22 component with respect to the u1 variable. And that would give us 2 times sine of u1 times cos of u1, which would also be equal to sine of 2 times u1. All the other metric tensor component derivatives would be 0 for all other combinations of ijk. So given these two facts, let's compute the Christoffel symbol for I equals 2, j equals 2, k equals 1. So we sub in 2 for I, 2 for j, and 1 for k. Now this derivative is the special non-zero derivative we have here, partial g22 by partial u1, and all the other derivatives go to 0. And looking at the inverse metric tensor here, in the second column, the only non-zero element is the 2, 2 element at the bottom. So this tells us that m equals 2 is the only m that we care about, because the g12 component just goes to 0. So we sub this term in for the g22 term of the inverse metric components. So this is the formula for the Christoffel symbol 2, 2, 1. And we can cancel the 1/2 and the 2, and we can cancel out one of the signs here. So we get that the 2, 2, 1 Christoffel symbol equals cos over sine, or in other words, cotangent of u1, which is exactly what we would expect. And that's also equal to the 2, 1, 2 Christoffel symbol, since we can swap the bottom indexes without changing the answer. Now let's try the I equals 1, j equals 2, k equals 2 case. So subbing in, we get this. And all the derivatives go to 0 except the partial g22 by partial u1 derivative. And now, in the first column of the inverse metric, only the g11 element is non-zero. So this tells us that we only care about m equals 1. So we sub this value in for the g11 metric component. And taking this result, we can turn all this into sine of 2 times u1, which gives us the answer that we were expecting. So if you work it out, all the other Christoffel symbols go to 0, and we get the exact same Christoffel symbols as before, except this time we computed them completely intrinsically without using the x, y, z variables. So the intrinsic formula for the Christoffel symbols gave us the same result as the extrinsic formula. And this isn't too surprising, since if we recall that the derivative of the gij metric component is given by this, and also recall that partial ej by partial ui is equal to partial ei by partial uj, when we compute this expression here, we get this. And after color coding the terms that are equal, the blue terms will cancel, the green terms will cancel, and the red terms will add together to give us this. So these three metric derivatives added and subtracted together are equal to this. And so you can see that when converting this into this and canceling the 1/2 and 2, we end up with the extrinsic formula that we're used to. So it's possible to start with the intrinsic formula for the Christoffel symbols and derive the extrinsic formula we saw in the last video. So to summarize this video, in intrinsic geometry, we can't make any reference to the outside space. So that means that there are no surface normal vectors and no position vectors. We require the basis vectors at a point to be the partial derivative operators of the coordinate variables at that point. And using the facts that the metric tensor is symmetric in its indexes, that the Christoffel symbols are symmetric in their lower indexes, and also using this special metric compatibility property, we can derive the intrinsic formula for the Christoffel symbols. And this works for both intrinsic and extrinsic cases. It's just that the intrinsic case only relies on the metric tensor being defined and doesn't depend on our ability to use the x, y, z variables in the outside space. And since the covariant derivative formulas end up being the same for both intrinsic and extrinsic spaces, the idea of parallel transport works the same for both. So this would be a vector getting parallel transported along the equator of a sphere, and this would be the vector getting parallel transported along a circle of latitude at a higher latitude. Now, I'm also going to throw in one last fact about geodesics. Again, I talk about geodesics a lot in videos 15 and 16, but the covariant derivative gives us a new way to define geodesics that we haven't seen before. So remember, geodesics are the curves we get when we just walk in a forward direction in a curved space. And we can define this idea of walking forward using the covariant derivative. The idea of walking forward on a curved space is captured mathematically by the idea of parallel transporting a vector along itself. So remember, parallel transport means that the covariant derivative of a vector is equal to 0. So when we say that a vector is parallel transported along itself, we mean that the vector that we're taking the covariant derivative of and the direction that we choose are the same. So when the covariant derivative of a vector in the direction of itself is equal to 0, the resulting curve that we get is a geodesic curve. So if our curve is a function of some curve parameter lambda, then the tangent vectors along the curve would be given by the derivative operator d by d lambda. So a geodesic curve is described by the covariant derivative of the d by d lambda vector in the direction of the d by d lambda vector, and the geodesic would set this covariant derivative equal to 0. So to take this covariant derivative, we just take the d by d lambda vector and differentiate it in the direction of the d by d lambda vector. Now we can expand d by d lambda out using multivariable chain rule and write it as a linear combination of these basis vectors. And remember, these are defined as the EJ basis vectors. Now to take the derivative of this with respect to lambda, we need to use product rule. So we get two terms, the first where we take the derivative of this, and the second where we take the derivative of this. Now, here we're just taking the derivative with respect to lambda twice, so we can rewrite it as a second order derivative like this. And to figure out what this second term means, we can again replace this d by d lambda vector as a linear combination of these basis vectors using multivariable chain rule. And remember, this is just like the EI basis vector. So now here we have two derivatives, and now we can turn this into a second order derivative, which differentiates with respect to uj and ui. Okay, so we have this expression here, and I'm just going to rewrite this and this using the vector notation for the basis vectors. It's still the same thing, I'm just writing it out slightly differently. And remember, we can expand these basis vector derivatives out using the Christoffel symbols like this. So subbing this into here, we'd get this. And finally, replacing this summation of j as a summation over k, we can factor out the ek basis vector and get this. And if you've watched my previous videos on geodesics, this formula should look very familiar to you. This set of differential equations are the geodesic equations. So any curve parameterized by lambda that satisfies these equations is considered a geodesic. It's just that now we're defining a geodesic to be a curve resulting from parallel transporting a vector along itself. And speaking in plain English, a geodesic is just a curve that we get from walking straight forward in a curved space. So it's like the straightest possible path in a curved space. Now, if this formula looks like a bunch of nonsense to you, I would encourage you to watch videos 15 and 16 to learn more about geodesics. I go through an example of finding geodesics on the sphere in video 16. So that was the intrinsic definition of the covariant derivative and a little bit of information on geodesics. In the next and final video on the covariant derivative, I will give you the abstract definition of the covariant derivative, which lets us take the covariant derivative of general tensor fields, not just vector fields.